Oh, whoops. All right. So we were organizing data into the form of a tree in this particular game. And we had some rules that we were following, right? So at the start of the game, you had a value like, say, 40. And as you added cards to your tree, they would go left or right according to their relative values. So if I were to add a 12, it would go left. If I were to add a 52, it would go right. And this structure has a recursive quality to it. So let's say I add a 5. So my 05 would go over there. That is, I insert it to my 40. It has to go left, but there's something there. I can't just stick it there. I have to see, oh, which way does it go from here? It goes to the left again. Similarly, if I add something like 24, 24 is less than 40, goes here. 24 is greater than 12, so it's going to go up here. Thinking in the other direction, if I have, say, 44, 44 is greater than 40, so it's going to go up here. 44 is less than 52, so it's going to go there. And then I could think about 56. 56 is greater than 40 and greater than 52. And so there it is. And this type of a data structure is known as a binary search tree. And something that I think is worth pointing out is that this phrase, binary search, we've seen before. Whoops. You know, that is binary, whoops, I'm resizing like crazy. Okay. Binary search was a technique we discussed for finding a value in an array. And the way that we employed that technique was look in the middle of the sorted array, and if the value we're looking for is less, we go left in the array. If the value we're looking for is greater, we go right in the array. A binary search tree, then, is the same basic idea, but structured as a bunch of link nodes as opposed to being in an array. So it's worth thinking about what are some of the pros and cons of this. One of the biggest pros of this approach is, much like the skip list, you can use a binary search tree to maintain a sorted ordering at all times. That is, whenever I did an insertion, I walk through the tree to find the perfect place for that value to go that maintains this sorted ordering. Removal is tricky. We're not going to talk about that till later. But insertion is pretty straightforward. There's also the interesting issue of how do you actually walk through it and display everything in sorted order, and that involves doing a tree search, as we're going to call it, and we're going to talk about that in a moment as well. But the big deal about this is to think about how many comparisons do we need to find a value and to insert a value. And so we're going to explore that now. The analysis is going to be hauntingly familiar in light of other things we've been looking at. So let's say I have n nodes in one of these binary search trees. Let's think about the possibilities here. What is the smallest possible height of the tree? How small can the height be if I have n nodes? How low can you go? That's like the biggest height I might have, right? So let's say I add things in an already sorted order. Okay, so I have 1, and then 2, and then 3, and then 4. Well, yeah, at that point, my height is going to be n minus 1. So that's the biggest possible height. And that's one of the extremes we were definitely going to need to look for. But what's the smallest possible height? 1. Well, assuming you've added n nodes, right? If I've added n nodes, I know that my height is going to be bigger than the constant. Yes.
Is it like n divided by 2?
N divided by 2 is a really important idea here. So let's think about where that intuition is taking us, right? If I have n nodes, here's part of how I could think about it. I would have 1 node at the first level, 2 nodes at the next level, 4 at the level above that, then 8, and then 16, and I could keep going. And ultimately, I'm going to reach a level where I do, in fact, have n over 2 nodes. So the bottom level has half the nodes. And the rest of the levels, if you add all of them up, are going to have the other half. Then you add them together, and of course you get n back. So now the interesting question is, so the n over 2 idea is very important. As you go from here up each level, you only got half as many nodes available. So the question is, how many levels are we looking at here? So here's part of how we could think about it. I want to know how many times can I divide n by 2 until I get down to 1. So I have n. I'm dividing it by half at each level to get to 1. Then I can divide both sides by n. I get 1/2 to the k equals 1 over n. Then I can take the reciprocals of both sides. So I have 2 to the k is equal to n. And now I can take the log base 2 of both sides. Using my log properties, k can move down here. That didn't really look like a base. There we go. That's more like it. And again, by our log properties, and really by the definition of the idea, we're saying 2 to what power is 2? Yeah. So the height of the tree with n nodes is going to be the log base 2 of n. This log base 2 just keeps coming back at us for some reason. And that reason is that the binary search tree is another example of this idea of using comparisons to break things in half. We've been seeing this idea a lot, and we're not really done with it yet. We broke in half our array in binary search. We broke in half our arrays in quicksort and heap sort. We did a different kind of decomposition with heaps. quicksort and merge sort, we split the arrays in half. With heaps, we divided it into everything smaller than me goes below me, or everything bigger than me goes below me. Splitting it in two every time, again, we had this log base 2 idea crop up. And now we see it again with the binary search tree. So what this means is that if we've got a nice balanced tree where it's completely filled in, inserting and looking things up is just going to be a log base 2n operation, which is pretty nice. And on the face of it, it's interesting to compare and contrast this with the skip list. We're not really relying on coin flips for this yet. As long as things get added in the right kind of order, then our tree is going to look really good. It's going to give us this log n insertion, this log n lookup. Of course, if we put the tree together in the wrong kind of an order, it could take linear time to add or remove. In this way, we can see a profound connection between the binary search tree and quicksort, right? So in both cases, if you pick a good pivot, if you pick a good value to be in the middle, you get a nice, predictable, balanced outcome. But if you pick the wrong value, bad things happen. Bad things happen. So I'll mention one kind of pseudo solution to this, which again relates to our discussion of quicksort today. And we're going to talk more about this issue in the classes that follow. I need to spend some time at the end of class going over project 3 with you all. But one kind of pseudo solution, right, is to do a randomized binary search tree. In other words, if you've got some stream of data coming in, you can imagine, just as with quicksort, that you could scramble the order. And if you're picking your roots at random, it's probably going to be a bushy tree, a nice log n feeling tree. The trouble is, this idea of a randomized binary search tree doesn't respect the idea of binary search trees as something you can update incrementally, something that things can come in and you can just put them right into place as they come in. It fails to respect that idea. That said, it gives us a neat perspective on quicksort. Quicksort is essentially an algorithm that forms an implicit binary search tree that's randomized within an array, especially if you do random pivot selection. So these are really, really similar ideas, but they're realized in very different ways. And the fact that the binary search tree is realized in a different way is going to give us some different pathways to thinking about keeping it organized and, more importantly, keeping it tight and low. So we're going to come back to this idea of the binary search tree next time on Friday. So any quick questions on binary search trees before we look ahead at project 3? All right, project 3 then. For project 3, you're going to be creating a project that does some animation in JavaFX. And here are the requirements. Your program has to have a GUI built with JavaFX and Scene Builder. It should be an interactive animation that uses the shape classes in JavaFX, which I'll be going over in a moment. Much like the last project, project 2, this should have some persistent state that you've modeled with a class. That is, there is some underlying data that's being represented by what's being drawn. program can use other JavaFX components, but the main focus should be on the interactive animation. It need not be complex, but it should do something interesting that holds the attention of the user. I have provided for you all, and actually give me a little time after class today to make the version of the zip file on the website be what I'm about to show you. So yeah, I have a little demonstration of how to do this kind of stuff in JavaFX, which I'm going to run for you now, so give you a feel for what this looks like, and then we'll talk about how I implemented it. So this is a little animation with some circles that bounce around. And they're different colors. And by itself, you know, it's kind of mesmerizing, but not terribly interesting. What really makes this fun is that you can click on a circle and move it around. And so when I click on the circle, I'm dragging it. It's going wherever I want it. I've changed the color so that I know that's the one I've grabbed. And then I can let it go. And I can grab another one. You know what? What if I make it bigger? All right, so now this is a little more interesting. I can drag one around and kind of let it go. And continue breaking up this little group. So one green, one left. And there they are, you know, adrift, moving around. All right, so let's walk through the various ideas and concepts that were involved in creating this. So this is the basic set up my JavaFX running thing code. It's not different really than what else you've done so far. Over here is a class I wrote called the ball class. The ball class is an interesting mix of code. To represent a ball, I needed a number of different ideas or concepts. The radius, how big is it? X and Y, where is it? So note that the convention within JavaFX is that we use doubles to represent positions on the screen. And that turns out to be really helpful. dx and dy, those are how far is this thing going to move in each of those directions on each time step. The circle is a JavaFX shape object. This is representing actually updating what's happening graphically. The pane is where that circle is being located. And then I have this little flag that indicates, does it wrap around like a torus or will it bounce? And so I have a constructor that sets all of this up. And I've got these setter variables here, setX and setY. These turned out to be important because I needed to have a way to tell the ball where I was dragging it to when I was moving with my mouse. Then I've got a way to change the radius. I can change the color. That too was really useful because when I dragged it, I changed the color to indicate that it was being dragged, which I thought was a nice feature of this program. Then, whoops, I can find out where it is. I can find out its radius. And then I've got this fairly crucial little method called move. And the idea of move was to update its position. And based on that update, figure out what it's doing. And that update required knowing the dimensions of the pane in which the circle was embedded. And so that's why I have that as an instance variable here. By having it as an instance variable, something that was valuable, right, was I actually changed the shape on the fly, and all of my circle objects behaved accordingly once I had changed it. So it's able to observe how the pane is changing over time. So then depending on whether I wanted it wrapping around or bouncing, I did different things to update it if it hit the side. And then here is a method called draw, which tells my circle, be the radius that you should be, then translate yourself to the X and Y positions that this data abstraction has determined for you. And that's an important idea because of this concept of move. So that's the ball class. This class is called juggler. And the idea of the juggler class is it's keeping track of all of the various balls that have been added to the application. And I maintain them in two different array lists. One array list is called juggling, and the other one is called weighting. So what's the idea? Juggling are the ones that the user has said, this is where I want you to go by moving it with the mouse. And those are colored blue. Weighting are the ones that were just kind of set up and deployed in the beginning that are waiting for the user to say, do something with this. And then I've got a way to handle the timer ticking. I'll go over that in a few moments. I want to go over a couple other things first. This drag method is a lot of fun. So a mouse event is a data type representing an interaction with the mouse. And where the mouse event comes from, I'll show you in a moment in the controller. But for now, I want to show you some key ideas. Elements within a JavaFX interface are just generically called nodes. And any mouse event is going to have some node designated as its source. What does that mean? It means that when you clicked on something, there was some object on there that received the click. So we then ask the question, what was the thing that received the click? And the find ball method handles that down here. So with find ball, it asks whether this node is a member of the given array list. And the way that I call find ball is I'm specifically looking for in the waiting list. So if I were to run this again, I can happily drag this and so forth, and it looks for it and has a way to find it. So yeah, so it asks, okay, is it waiting? And if it's waiting, in other words, it belongs to that waiting list, it checks every element of that list, and if it's that object, I actually return an optional of that, and if it's none of them, I return an optional.empty. This enables me to do something that's kind of fun with optionals. Optionals have this method called if present. So if you invoke if present on an optional, you can give it a little block of code that it's supposed to execute if that's true. And so this block of code is what's called a lambda expression, which is a handy way of concisely expressing code, where I say if it's present, this variable gets the value that's inside the optional. And then I have an arrow and a block of curly braces. That's a block of code that's actually a parameter to this method. So in other words, if it's present, remove it. Oh, whoops, over here on waiting. If it's present, remove it from the waiting list, add it to the juggling list, and change the color to the Dodger blue. Let's see, wait, which one was that? Oh, that was released. I went down too far. Sorry about that. Drag is where we were. So if it's present, we're going to set its x to what its x was plus the x of the event. And then similarly, the y, we add the y of the event. Why is that? A drag is a mouse event that represents the mouse moved from here to here. So that mouse event is representing an update to position. I also have handlers for releasing and pressing the mouse. So when I press the mouse, I remove it from the juggling list and I add it to the waiting list. When I release the mouse, I release it from the waiting list and add it to the juggling list. The juggling list are all the balls that are moving. The waiting list are the ones that are under control of the mouse, in essence. So that's doing stuff with the mouse, but there's this question of, well, how do you talk to the mouse to begin with? That brings me back to the controller. And here in the controller, I have created a juggler object. And in my initialize, what I've done is set up these event handlers. So I create 10 circles. Each one, I make it green. Remember, they're all green at the start in that little routine. I set the stroke to be black. So in other words, as I continue to draw stuff, I want it to be black by default now that I've made those things green. And then I tell each circle, when the mouse is dragged, I want you to call the juggler.drag method. So what I've done here is set up what's called an event handler. So the mouse getting clicked is an event, or when it gets dragged, I get a mouse event, and I want that passed to juggler.drag there. When the mouse is pressed, I want that event sent to juggler.pressed. When the mouse is released, I want it sent to juggler.released. And then I go ahead and add the ball, and I use a little formula with the index so that they're staggered and they're not all right on top of each other. And there they are. And that's how I set up those mouse event handlers, which is a lot of fun to do. Keyboard handlers are also possible to set up, and I might modify the demo to show how to do that as well. But the keyboard's a little tricky. And the reason it's a little tricky is any user interface has to arbitrate which of the objects that are on the interface gets the credit for the keyboard. In other words, which object actually gets to handle it. With a mouse, it's completely unambiguous because it's just wherever the mouse pointer is literally located at a given time. Keyboard's a little trickier. I might go over that a little bit on Friday, just for fun. So last thing I wanted to show you, make sure to go over with you today, was the timing. And so I created a class that extends animation timer. Animation timer is something that's part of JavaFX. So key ideas with the animation timer. You override a method called handle, and that method takes a parameter that's of type long, which is the number of milliseconds since your computer started up. So you don't really know when this timer is going to tick. At some point, the JavaFX system just sets these things off. You can assume it's pretty rapid. In fact, it's probably more rapid than you actually want. So what I did here was I wrote some code to see, has enough time passed since the last time this was triggered? So I've got this instance variable last, which I initially set to 0. And then I've got this variable called interval. The idea of interval is I figure out how many frames per second do I want? How frequently do I want to update this? The L at the end means a long literal. Okay, and so a long is a 64-bit integer, as opposed to an int, which is 32 bits. At least one of you discovered in lab yesterday, 32 bits can actually run out fairly quickly. We had one student who had an infinite while loop where one kept getting added to an int, and then it overflowed and became -2 billion, and he was like, what happened? I never subtracted. So a long takes a lot longer to do that at 64 bits. No pun intended, although if I had thought of it, I would have. So I work out how many frames a second do I want. And then because I am dealing with it's actually nanoseconds. I take a billion and I divide it by that frames per second, and that gives me the interval. In other words, after this many nanoseconds, this is when I want things to happen. So, briefly going over that then, I just subtract this current timestamp from the last one that I updated. And if it's greater than the interval, it's time to update. And so then I move and draw all the balls, and I reset the interval start time to be now. So now another number of nanoseconds has to elapse before I come back around. And then to kick that off, back in the juggler class, I used the start method to tell it to start. And that's what kicks off the animation. So this particular example shows animation both by using a timer and using the mouse as a means of user interaction. And I think for this first project in which you'll be dealing with interaction and animation, you'll benefit by mainly sticking to the mouse. The keyboard, like I said, is tricky. If you really, really want to do keyboard, that's fine. And we can talk about that. But I think it'll be a little easier to focus on the mouse for now and think about what the mouse can do for you. So that's project 3. It'll be due a week from Friday. A week from Friday. So as with all such projects, as one of my professors put it back when I was a student, start early and start often. All right, see you Friday.